Okay, practice 11.3. These figures are, well, I've got two kites and I've got a rhombus, but the area formula for both of them is the same. The area is 1/2 of diagonal 1 times diagonal 2, so half of the product of the two diagonals, okay? So looking at this first problem, they give me the length of both diagonals, so I just have to plug them in. So I'm taking half of 15 times 27. Let's see, 15 times 27, half of that. And it's going to come out to 202.5. I don't know what the units are, but I know they're square units as its area. Okay, so there's my first one. Second one, I also have the both diagonals, so 1/2 of 12 times 9. Well, half of 12 is 6. 6 times 9 would be 54. That's that many square units again. Okay. This next one, let's see. I don't actually have all of the pieces, but if you remember back some of the properties of kites, this diagonal is clearly not bisected because I've got that little piece and the long piece, but the other diagonal is. So if this is 7, this is going to be 7 as well. So one of my diagonals then is going to be 14. That one. Okay, so that's nice. And then what is that 16 referring to? So that's a good question. So I'm interpreting that the 16 is this piece. But maybe it's supposed to be the bottom. That's not a very clear diagram. Let's say it was the bottom. Well, then I could use the Pythagorean theorem because those are going to be perpendicular, right? Because that's another thing that happens with kites. So yeah, it's not very clear, but if the 16 was the hypotenuse, I could still find this leg with the Pythagorean theorem. I'm just going to assume the 16 is this piece, which means that my other diagonal is 18. So I'm going to use 1/2 of 14 times 18. Sorry, that's a bad diagram there. So it's not clear what the 16 is referring to. So let's see, 7 times 18 is 126. Okay. So yeah, if you interpreted the 16 differently, well, that'll give you a different answer, but still 1/2 of diagonal 1 times diagonal 2. Okay? All right, next up, find the measure of a central angle of a regular polygon. It's really important that it has to be a regular polygon with the given number of sides. Okay? So I'm not going to draw a nonagon here, but let's just pretend that this is the bottom of a nonagon. Okay? So a central angle is any angle that is formed when you connect two radii that go to the two radii, which are the segments that go to the vertices. Okay, so this is what I'm looking for here, that angle. Okay, so all I'm thinking is, well, since there's 9 sides, there's also gonna be 9 central angles, and since it's a regular polygon, all of those central angles are gonna be the same. So all I have to do is I know all of the central angles, all of the slices of the pizza together are 360 degrees, and there's 9 of them of equal value, so I just take 360 divided by 9, and that's going to give me 40 degrees. Okay, so with 16 sides, it's the same kind of picture, except now there's going to be 16 slices, so the 360 is going to be cut up into 16 equal slices. And that gives me 22.5. Okay, and with 20 sides, got 20 equal slices, which gives me 18 degrees. 18 degrees. Okay, moving on. Find the given angle measure. They tell me again that this is a regular hexagon. That's nice because that means all of the central angles are congruent, all the sides are going to be congruent, and so forth. Okay. All right. So let's find the measure of angle CGD. CGD. Find the measure of this angle. Well, this is a central angle for the hexagon. So hey, that means it's going to be just like in these previous problems. I got 360 degrees cut up into 6 congruent pieces. If you put in all the pieces of pizza, We got 6 slices there. These are half slices, right? So 6 complete slices, so 60 degrees. Okay. All right. So next up, HCG. Where's H? HCG. So that means I want this angle. This little shaded one, HCG, is right there. So what I can do here, I'm going to, this is kind of small, so I'm going to make an enlarged version of that half slice. So for that half slice, well, I knew this whole angle was 60 degrees, so that means for the half slices, that's going to be 30 degrees. Oops, 30 degrees. So now I've got 30, 90, that means this must be 60. Okay, so yeah, this is 60 degrees then. Okay, CGH is the 30-degree angle there. Already figured that out. Okay, and then EGC. Well, EGC is 2 of these full slices. Each slice is 60 degrees, so I'll just double that, and that means I got 120 degrees there. Okay. All right, and now moving on to the next page where the we get down to some serious business. Was that off screen the whole time? Oh shoot! I think I had that off screen. My bad. I had enlarged that, and I think it was off screen. Oops, there it is. Okay, so I'll try to leave at least that little piece on for a second. Okay, next up, I've got a regular polygon here, and I'm finding the area. So there are 2 ways to do this problem. One way, there's an area formula for where it has to be a regular polygon. My area formula is going to be 1/2 of the apothem times the perimeter. Okay, the apothem is going to be this segment. It's going to be 3 here. The perimeter is the distance around the outside. Okay, so that's totally fine. I don't have the perimeter yet, but I can find it with this information. So I can do, this is going to be 1/2 of 3 times whatever the perimeter is. Okay, so that's one way to do it. Another way is to just think about triangles. Now, like if I'm thinking about slices of pizza, if this is a slice, if I can find the area of this slice, I'm just going to multiply by 6 because there's going to be 6 slices just like that. So either method is totally fine. It doesn't matter. It's the same amount of work really because I'm going to have to find the perimeter, and in order to find the perimeter, I'm going to have to find this piece of crust here, this like crust for this half slice, okay? So what I'm thinking is, well, a whole slice, there's 6 slices just like this, right? So it doesn't really matter if you draw them in or not, but 6 complete slices. And then, so I know each of those, 360 divided by 6 would be 60 degrees, and that means that this is going to be 30 degrees up here, okay? So then I'm thinking, oh, wait a second, this is a 30, 60, 90 triangle. I've got the long leg. If I want the short leg from there, I'm going to divide by the square root of 3. This is from a couple chapters ago. Okay? And then I can multiply by root 3 if I want to put this in simple radical form, root 3 over 3. So that gives me 3 root 3 over 3, which simplifies to just root 3. Okay? So remember, that's for my half slice. So then the whole slice, I would double that, okay? So I'll write it over here. So if root 3 is the crust on a half slice, the crust on a whole slice is going to be 2 root 3, okay? And then I can find the whole perimeter. So my perimeter is going to be, I'm just thinking 2 root 3 times 6. There would be 6 pieces of crust, right? And so that's going to give me 12 root 3. And now I have the perimeter that I can put in here. Also, you can imagine you can find the area of one of these triangles now, right? Because 2 root 3 would be the base, 3 would be the height, so you can do 1/2 base times height. Find the area of your slice and then multiply by 6. But that's going to get me the same result as this over here. So let's see, I'm thinking 1/2 of 12 is 6. So 6 times 3 is 18 root 3. I don't know the units, but I know they're squared. Or you could do a decimal approximation of that as well, okay? All right, so that problem, I used a special right triangle because anytime you cut up a hexagon, a regular hexagon, you'll get equilateral triangles. And then the half slices then will be 30, 60, 90s. Okay? But that's not going to work out so nicely always with other figures. So let's see, this stop sign shape. So this has 8 sides. This is an octagon. Okay? So I'm still thinking 1/2 apothem times perimeter, or I can find the area of one slice and multiply by 8. Now this time I don't have the apothem because this is a radius here. Okay? So let's think about this slice here. This is going to be my apothem, right? I'll put a little A there. Okay? So here, let's draw in a second slice just because it's going to get too crowded there. But this central angle here, I'm thinking, okay, there's 8 slices just like that. So I'm taking 360 degrees divided by 8. That means I've got 45 degrees for that central angle. Okay? So let's take out, I'm going to take this out because it's going to get a little crowded in there. I'm going to just draw this half slice bigger. Okay, so if a whole slice is 45, then half of 45 is going to be 22.5. So now I know that's 22.5. Okay, I've got the 14 there. So now I'm thinking, well, how could I get that apothem? Well, what I can do is use trigonometry. I can use SOHCAHTOA, right? So if I'm down here at the 22.5 degree angle, then I've got, this would be the adjacent leg, and this would be the hypotenuse. So I'm thinking sine, cosine, or tangent. I'm thinking cosine, because adjacent and hypotenuse, right? So I can say the cosine of 22.5 degrees is going to equal apothem over 14, okay? So I'll multiply both sides by 14. And I should say degrees here. That's important. I forgot that. Okay. So I'm going to put that in my calculator. So I want to be in degree mode in my calculator. Let me make sure. Oh, I'm in radians. So let me switch that to degrees. I was assuming it was going to be in degrees, but it wasn't. Okay. Now I'm in degrees, so I'm going to put in 14 cosine of 22.5. Got about 12.93. So my apothem is about 12.93, or it's exactly 14 cosine of 22.5 degrees. Okay, so there's my apothem. All right. So we remember our formula we're using here. My area is the same formula from the previous problem: 1/2 of apothem times perimeter. Well, now I've got the apothem, but I still need the perimeter, okay? So the perimeter I can find by getting this piece of crust. So let's just call this x. So if I'm looking for x, I got 2 options now. I could do Pythagorean theorem since I've got those 2 sides, or I could do another SOHCAHTOA problem. I'll do SOHCAHTOA. So this would be opposite, and I'm going to use the hypotenuse, so I'll do sine. So sine of 22.5 degrees equals x over 14. And then it's time for my calculator again. So 14 sine of 22.5 degrees is about 5.36. Okay. So 5.36 then, remember that's just this bit, right? This bit is 5.36 roughly. So if I wanted a whole crust, I'm going to double that, right? So let's take that nice long decimal, double it, and that's about 10.72. And then for my perimeter, I'll do a little side problem down here. From the perimeter, it's going to be about, well, there's going to be 8 slices, and each one of them has a crust that's 10.72 units long. Still got that 10.72 number in my calculator. Let's multiply that by 8. We've got about 85.72. Okay? And that's the final piece of the puzzle there, right? Okay, and now I just multiply all of this together. I'll just use that whole decimal there. So I'll multiply that by 0.5 and then by 12.93. And that 12.93 is rounded again. So this is approximate, but it's going to be about 554.19. And I don't know what the units are, but again, I know they are square units. Okay, so these problems can be pretty involved because you got to bring in a lot of knowledge from previous chapters, like the trig, right? You got to remember how to do the SOHCAHTOA stuff. Sometimes when you cut these up, you'll have special right triangles, and you could use that. I could have used SOHCAHTOA on the last problem too. I just used the 30, 60, 90, but I could have done SOHCAHTOA as well. Okay, and that's it for this time. See you later.